Thank you, Mr. Chairman, for the nice introduction. The last few years, my group has been working on a new modulation format for short-haul applications called mode vector modulation. Mode vector modulation is an extension of Stokes vector modulation for multi-core or multi-mode fibers, or for free space communication using multiple modes. The advantage of mode vector modulation is that it can be used with a direct detection receiver, and in this talk we propose a new improved design of a direct detection receiver with complexity that scales linearly with the number of modes. Before I start, I would like to acknowledge the contribution of all the co-authors on this paper. For those of you who haven't seen previous presentations of my group, I have some introductory slides on mode vector modulation. In the main part of my talk, I will focus on the design of mode vector modulation receiver, and at the end I'm going to show numerical results about the performance of various types of mode vector modulation receivers. Moving to the introduction of my talk, I have here a slide that explains the operating principle of mode vector modulation. Let's assume that we have an ideal homogeneous multi-core fiber with single-mode cores. This fiber has 4 degrees of freedom, the x and y polarizations of each core. The mode vector modulation consists in launching the same pulse, but with different amplitudes and different carrier phases at all the spatial degrees of freedom. The signals are multiplexed pairwise and launched in the x and y polarization of each core. If we have k cores at our disposition, we have n equal to 2k polarization and spatial degrees of freedom that can be used as a parallel bus jointly rather than independently, as in the case of space division multiplexing, to create energy efficient spatial modulations. On this slide, we see intensity patterns for 16 different symbols that can be launched over a 2-core multi-core fiber. Since we have 4 spatial and polarization degrees of freedom, we call this particular instantiation of mode vector modulation 416 MVM. The intensity patterns don't show the whole picture of mode vector modulation, since we miss the information about the differential phases between the carriers launched on different spatial modes. A more complete picture is to show the intensity pattern and also the polarization ellipses for all possible distinct combinations of degrees of freedom. So for 4 spatial and polarization degrees of freedom, we can plot 6 polarization ellipses. Keep in mind that the number of polarization ellipses on this modulation format scales quadratically with the number of degrees of freedom, and this will explain why the polarimetric receiver we have at our disposition scales also quadratically with the number of degrees of freedom. Moving now to the receiver design, I start from the case of 2 degrees of freedom, a single mode fiber, where mode vector modulation has a special case Stokes vector modulation. Here I show a polarimetric direct detection receiver, where the incoming signal is split into 3 branches, and each one of the branches measures 1 Stokes component. The design, for example, can be found at the paper listed at the bottom of the page. I have the same receiver design here for SVM, simply there is a rewiring of the photodiodes, and the DSP, instead of a Stokes vector, rearranges the same components in a cross-correlation matrix between the Jones components called a dyad. The dyad and the Stokes vector have identical information, so in the slides that follow, I'm going to use a dyad instead of the Stokes vector. I also want to mention that the polarimetric receiver for SVM can be implemented using a 90-degree optical hybrid. More details can be found in several articles. I list here the article by Tanemura and collaborators at ALT in January 2020. This type of receiver can be integrated, for example, using silicon photonics. I move now to the case of n larger than 2. So mode vector modulation. Here I show the pulses launched along the different spatial degrees of freedom. The amplitudes and phases of these pulses can be combined together into a generalized Jones vector with n complex components. Each one of these components has the amplitude and the phase of the pulse launched at a certain degree of freedom. So we have n complex components and 2 n real parameters. The same information can be represented equivalently by a Stokes vector. A generalized Stokes vector has n squared minus 1 real components, and it can be obtained by Jones vector by using a quadratic transform. Since the Jones vector depends on 2 n real parameters, the Stokes vector depends also on 2 n real parameters, and therefore the Stokes components are interdependent. Keep this in mind because we're going to use this property in order to simplify the receiver design. If we plug the form of a Stokes of a Jones vector into the quadratic form that gives a Stokes vector, we see that n square minus 1 Stokes components can be grouped into three different types that are shown in general form here. We have the real part of the cross correlation of Jones components, the imaginary part, and the square moduli of Jones components. We have seen that you can measure the real and the imaginary part of a cross correlation term by using a hybrid. So since we have n times n minus 1 over 2 such terms, we can use an equal amount of hybrids with 4 photodiodes per hybrid and add n photodiodes due to the measurement of the square moduli for a grand total of 2n square minus n photodiodes. We see that this simple back of the envelope calculation shows that the mode vector modulation receiver needs a number of photodiodes that scales quadratically with a number of degrees of freedom. This is prohibitive because a coherent receiver, for example, has number of photodiodes that scales linearly with a number of degrees of freedom. Therefore, for a cost-sensitive application like short haul, the number of photodiodes must be reduced. I show here the improved receiver design, where we take into account the interdependency of Stokes parameters in order to reduce the number of measurements. But now we have measured only the elements that are shown in color in the diodes. Here I show an example for n equal 4 for a 2-core multi-core fiber. The black elements can be inferred by the elements in color. So here is the unit cell of the mode vector modulation receiver taken by the article of Tanemura. We can concatenate n-1 unit cells to measure only the cross correlation between the terms that differ by one position in their index. We need a grand total of 5n-4 photodiodes using the diode recovery algorithm that I list here. You can read the details in the paper because I'm running out of time. So moving to the validation of the performance of this improved receiver design using Monte Carlo simulation, we have studied the case of a 2-core multi-core fiber, and we have 4 degrees of freedom. We are interested in preamplified detection, and therefore we are working at the ASC noise limit. And I show here results for different constellation cardinalities, where different color points indicate different types of receivers. We notice that the improved receiver design has the same performance like the original receiver design that uses a lot more photodiodes. And we've verified the results for the case of a quad-core fiber. In conclusion, my group has proposed recently a new modulation format that is intended for short-haul applications, and it is energy efficient because it uses multiple spatial dimensions. The complexity of the most rudimentary receiver, however, for this modulation format has complexity that scales linearly, quadratically with a number of degrees of freedom. In this presentation, I showed you an improved receiver design with front-end complexity that scales only linearly with a number of degrees of freedom, and I proved that this decrease in complexity does not result in any decrease in performance, at least in the case of the ASC noise limit. I would like to acknowledge the generous contribution of our sponsor. I would like to mention that this work is part of a larger project on hybrid classical quantum networking using multi-core fibers, and you can find more information by clicking at the link below. Thank you for your attention.